until you see those probabilities, which might be kind of hard to do, honestly. It might take us a lot of trials to do. What I've done is I've set up a similar spreadsheet to yesterday with Excel, where Excel now rolls 2 different dice, and then adds them together to get a sum. So every time I press F9 up here, you're going to get another die roll, and the distribution will start to fill in. We're going to let this thing kind of play out here. I'm going to try to figure out if I can figure out some way of holding it down while it's doing its thing. Let me get a speaker. I forgot my stapler, which I usually use to hold it down. You can hold it down for you. Say that again?
Do you have tape?
I don't. That's a damn good idea, though. Keys. Didn't bring them either. A box of staples. That might be heavy enough. Let's try this.
You have keys over here.
We got it. I know the keys, there they are. That's okay. This actually working just fine. So you're seeing some corrections as it updates every so often. But what I want you to focus on is I grayed out some stuff. I just gave a talk on this at a conference, how to set up, these are called iterative calculations. So every time it's rolling 2 dice and adding it up, you're seeing this little 1 right here flip through red. That's telling you right then at that moment what was rolled. And then this column here increases by 1 for every one of those reds. So each time that column turns red, that number goes up by 1, 13, 14, 15, and so forth. So what you're seeing is, hopefully, we're going to see a connection between what it's getting and what we got over there. So the first thing I want to do is I want to look at these. Do these make you happy? Right here.
Yeah.
Die number 1, die number 2. Why do they make you happy? Because that's what they should look like, yes? Each of those dice should be rolling 1/6 1s, 1/6 2s, 1/6 3s, 1/6, and so forth, and so on, and so forth, and so on. Now let's look at the overriding curve up here, which is graphing the sums on the 2 dice. Now notice where the 1s, most of the ones that are happening near the middle, and then every once in a while 1 happens at the ends. Does that make sense with our distribution?
Yes.
I think it does, doesn't it? Because we just showed that it's more likely to get a sum near the middle of the distribution than it is to get it at the ends, because there's more combinations, as Zach pointed out. So let's see if these percentages sync up with our percentages over there. It's saying there's about between a 2 and a 3% chance. Looks like maybe closer to 3, high 2, low 3% chance of getting snake eyes. The problem is we don't have it in percent, we have it in fractions. 1 in 36. That should be a little bit below 3%, yeah?
Yep.
1 in 36, a little bit below 3%, because 1 in 33 would be 3%, I think. I think I'm doing my math right in my head. So 1 in 36, a little bit below? Well, it's rounding to 3. It's having a hard time deciding whether it should be 2 or 3%, but it's close to 3%. Well, yay! That makes perfect sense, doesn't it? We then said it was twice as likely to get a 3. Does it look like it's about twice as likely to get a 3? Now, you got to realize that's, again, rounded, right? That's, again, rounded. But if you double it, the 5 is about double 3, or 5 or 6, whatever it's going to fluctuate out to. This is 9%. It's showing as 9. It should be 3 out of 36. 3 out of 36 is 1 out of 12. And that's just about 8%, actually. So that's a little bit high right now. Notice how 8% is showing down here. 8% is showing here. I'm going to bet that's going to fluctuate out as we let it roll. And this is the whole point of on average over time. We have now rolled these things about 6,000 times. I want to continue to let them go. Keep going to let these go for a while while we're talking. Oh, there it's flipping around again. It's flipping now. It's trying to correct itself. 11, 14, 17, 14, 11, 8, 5, 3. It's following our pattern almost beautifully, yes? So this is kind of slick. You see the distribution? It's not a bell curve. It's a TP distribution. It's the only distribution I found in probability that actually looks exactly like a triangle. It's not bell curved. It goes up linearly. For every slope, talking about grade, Math 105, here we go again. For every 1 over, it goes up by a 36th. So you've got this like triangle that's shaped like this, perfectly sloped, and it starts going back down again. It's got an equation. You don't want to see it. Maybe you do. If you want to see me start after class, I'll give you the equation for it. You can actually generate the equation. It's fun. So let's let that keep playing, and we'll come back to it. What I want to do right now is I want to analyze the distribution with summary parameters. For example, what is the numerical average of this distribution? What is the numerical standard deviation of this distribution? What would you call the outliers in this distribution? See, that's what I want to get at now. So good. Eric's like, oh, I like this up till the moment he mentioned all that crap. So what I want to do is I want to be able to identify what these parameters of the distribution are, because then we can start talking about how likely or unlikely the other parts of the distribution are, and should we even consider betting on them or betting against them. So let's do this. Let's do this. I can get rid of this 2 for now. All right. So, this is still experiment number 2. Continued. What is the average sum that we get? And what is the standard deviation around? Is it okay to use? I think it's okay based on that graph to use a standard deviation. It's not highly skewed. It's pretty symmetric. It's not bell-shaped, but it's pretty symmetric. So I'm comfortable using it. You guys okay with it? Maybe?
Yes.
I know it's close to lunch and your brains are starting to drain before eating lunch. I apologize. But I'm okay with it, yes? I'm totally fine with it. I'm totally fine with it. So let's get some numbers up here. Oh crap, I have to get this.
What's that little thing, sign on the bottom again?
What is that?
Little
Your
sigma.
little sigma, that's the population standard deviation. And don't worry, Kelly, you're about to see why I don't have to worry about it, because your TI is going to give it to you and there will be no confusion as to what it is in a second.
I like that news.
Say that again?
I like that news. I don't want to worry about it.
You don't. You don't. It's practically not going to be an issue for you, only because you're about to see your TI will give you exactly what you need and nothing more.
Okay.
Which is nice. It's one of the nice things the TI does. Hang on 1 second. Let's get this bad boy in here. 2, 3, 4, 5, 6, 7, 8. I'm just putting the distribution in the TI, friends. And then we got 1 and 36. Your TI automatically changes things to decimals as it goes. So notice these are agreeing pretty well with what we were seeing up there on the Excel spreadsheet.
So can you just put the 1 or 2 that doesn't not the same as the decimal?
Say that again.
So I just put 1, 2, 3. Like for my
Oh, the frequency, Zach. Okay, so it's what Zach put in. He put 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, and not the fractions. The problem with that is it won't be much of a problem, my friend, except for the fact that, well, let's take a look. Run it your way. Run it your way. No, it is, but run it your way, and you'll get something that I just told Kelly she wouldn't have to worry about. And I want to make sure that you see what the difference is. Okay, so I put it exactly our distribution over there. I'm going to run 1 bar stats on it now. Mine's in L4 and L5, I've got to remember that. 1 bar stats, L4 and L5. Here we go. Zach, you've got something right there that we don't. And this also says 36. So the reason I like doing it this way is I can check my distribution to make sure I set it up correctly. If this sums to 1, or essentially very close to 1, it means my probabilities sum to 1. You have to kind of make peace with how your TI talks about this. When it says summation of n equals 1, it really doesn't mean that. It means the summation of the probabilities of x equal 1. You have to kind of make yourself believe that, because the TI isn't smart enough to know it's a distribution of probabilities. It's a dumb computer. It just knows you're putting numbers into it and getting numbers out. So when you see n equals 1, that means you put it in correctly. Now Zach, you put it in correctly because you got 36. So you put all 36 outcomes in. The problem is you also have something here, a sample standard deviation. See, Kelly, it's only giving you this. That's the standard deviation of your population. That's 2.4 plus or minus from the average. Now remember, I gave you this warning, I think on Thursday of last week. It calls it X bar. It should really call it, but it won't. It should really call it, but it won't call it mu. That's a mu. Mu. There we go. Mu. So the TI does not know, everything else you can ignore. None of this stuff is meaningful except for the standard deviation and the average. So it's just, we kind of have to adjust the way we look at the results of the screen that the TI gives us. So we know the average roll that we're going to get is a 7, hence Aaron's lucky 7, right? Hence the lucky 7. Hence why craps is so appealing, right? Because if you bet on you do a past line betting craps, and you throw the dice, you win automatically if you get a 7 or an 11. They even sweeten the pot. They say if you roll a 7, and you know what, or an 11 too, you win off the bat. So they make it even better for you, because they added the chance of an 11, which is 2 in 36. So a 6 in 36 for a 7, but they make it 8 in 36 because it's 7 or 11. And you're like, hot damn! And then you realize, wait a minute, 8 in 36 is still less than 50-50. But then they sweeten the deal even further with craps. And they say if you don't roll a 7 or 11, but if you do roll a 4, 5, 6, or 8, 9, or 10, all you gotta do is roll that again before rolling a 7, and you win again. And you're like, hot damn! I can win all those ways? And they say, yeah, the only way you don't win is if you roll snake eyes on the first roll, which is bad. But that hardly ever happens, right? And if you roll a boxcars on the first roll, but that hardly ever happens. Or 3 on the first roll, but that hardly ever happens. Hell, 2, 3, 12, what does that happen? 4 out of 36 at a time? Ignorable, right? Oh, and by the way, you also lose if you roll a 4, 5, 6, 8, 9, or 10, and then roll a 7 before you roll that sum again. But just ignore that. And it's great, because you actually calculate the probability. Remember what the probability was from 105? Do you guys remember? It's like 49.2% chance that you win. That's that close to 50. It's genius. There's only one game of chance in Vegas with slightly better odds. You know what it is? The roulette wheel. Slightly better, not much better. Craps and roulette are the best ways to lose your money as slow as possible. Just keep betting past line. Keep betting past line. And if you bet don't pass, it's slightly even better, but it's still below 50. So you can lose your money nice and slow while they continue to give you free drinks. Amazing. We'll analyze that in a quiz in 2 weeks. I got a nice little quiz ready for you guys, ready to go. It's a fun thing to analyze. So anyway, your average is 7, plus or minus 2.4. So using those numbers, what would be called unusual sums to get? What would you call an unusual sum to get?
1 or 12.
Say that again.
1 or 12.
1 or 12, or how about 2 or 12? Because you can't roll a 1. You meant 2. So Zach says, using those numbers, the outside points are the most unusual, the 2 and the 12, yeah? So Zach, I'm guessing you did a quick mu plus or minus 2 sigma. I'm thinking that's what you did. So what he did was he did mu plus or minus 2. He did 2 standard deviations. Does that make sense to you guys? Mu plus or minus 2 sigma? Which is the same as x bar plus or minus 2s. I'm just using the number we got. So that's 7 plus or minus 4.8, excuse me. Fair enough? Plus or minus 4.8. 7 plus 4.8 is 11.8. 7 minus 4.8 is 2.2. So anything outside of 2.2 to 11.8 would be considered an unusual sum. Well, 2 is a little bit outside of 2.2, and 12 is a little bit outside of 11.8. So that sounds to me like they would be considered the unusual events. Now some of you, as soon as I mentioned that, you got pissed. I'm sorry. I saw a lot of faces were like, I'm with you now. I'm not happy anymore because now you're talking about this 2 standard deviation. So there's an easier way to measure outliers. I told you last week there are 3 ways to talk about outliers. And how many ways did we talk about them last week? 2. We did. That was one of them, right? That was one. The second way, remember what the second way was? The little box position. Start the box plot. Box, 50%, stack. And that's a fairly common one too. But by and large, the most common way of measuring outliers is tied to distributions of probabilities. Here we go. You ready? Outlier ID method. Number 3. And this is actually kind of it's the underpinnings of Math 244. Honestly, this outlier ID method right here is kind of what Math 244 is built around. The general statement of it is, tell me what an outlier is again. What is an outlier?
It's the furthest, what's it going to happen very often?
That perfectly said, Jennifer, thank you. And when you said furthest, I love what you just said. Because it's where they usually are, is on the ends.
Yeah.
But believe it or not, they can happen in the middle. And you'll see how, as we go through this course, you can have data sets where there are outliers in the middle. But the way you rephrased it was beautiful. They don't happen very often. That means we call them, use another word, use a non-mathematical word. If something doesn't happen very often, we say that it is infrequent, like that. Infrequent. Ooh, I like that word better than what I was thinking of. And here's why, Katie. Because infrequent ties in the word frequency. Infrequent means it doesn't happen very often as a percentage of the time. Haven't we been measuring that with these new distributions? That probability column, yes? That probability column is telling us the frequency of occurrence of something. Oh, that's good. Thank you very much. So, how do you call something an outlier? Well, if it's infrequent, when it's infrequent or rare, and now the question is, I'm putting those in quotes, aren't I? Yeah. Why am I putting them in quotes?
You don't know how to define that.
How do you define relative infrequency? So what I'm going to teach you guys, starting, how many of you guys take a 244 as well? It's a discussion we'll start now and continue for the next, whenever we have time, and then in 244 also. Infrequent is defined statistically as a probability that's less than 5%. That's almost the gimme, the p-value argument of 5%, that's infrequent. That's the definition that's commonly used there. I'm not saying it always should be, I'm saying it always is. That's what's generally in research. Sometimes there's a good reason not to use that, but that's what infrequent is called. So, if any probability of x is less than 5%, if it rolls in less than 5%, that means that x is rare. The event x is rare, which means the event x determines an outlier. What I love about this is the fact that that agrees with what Zach just did. Zach just said that 2 and 12 are the outliers because they're outside of 2 standard deviations, yeah? Well, 2 and 12 are also the only 2 probabilities in that distribution that sneak in under 5%, aren't they? They're about 3%, a little bit less than 3% each. Isn't that cool? Isn't that cool? 95% of the time, you get 3 to 11. You only get the extremes 5% of the time, a little less than 5, a little bit more, I guess, than 5% of the time. Let's look at how Excel's doing. Let's see if you can see that definition right now. There we are. Oh, it just shifted a little bit. You see that? When I turned it back on, one of the bars just changed. That guy's still stuck at 9%. He'll correct himself over time. But look at that. And the only ones that would be termed outliers are outside of those 2 standard deviations right there, yeah? 1 standard deviation, 2 standard deviations. Pretty slick, huh? Zach, go!
Less than or equal to 5%?
Well, that becomes an argument I don't think we should have. Did you hear what Zach just said? Fantastic question. Should it be less than or equal to 5% or just less than 5%? The problem with that is, because of the continuous nature of this axis, any one point on the axis is technically infinitely thin, so infinitely immeasurable. You can only deal with it from a range of values. We'll come more on this in about 2 weeks. So it's an argument I don't want to get into because it really does, we don't get anything from it. If it makes you feel better, for sure, absolutely, put it on there. Put it on there. Now you might look at this and say that's 5%. Well, technically speaking, it's rounded to 5. It's above 5 and it rounds down to 5. So I don't want to get in those fist fights either. Does that make sense? And honestly, if it gets that close, you'll learn this in 244, when this probability gets that close to 5%, you start taking closer looks anyway. So, cool? Notice it's corrected to 8, that's back up to 9, it's trying, it's fighting its way back down. Slowly, it's fighting its way back down. Let it keep rolling, keep rolling. Ask me questions right now, we'll put it back on at the end of class. Ask me questions right now. Please, if you have them. Aaron, go, yes.
I have one from Thursday that I've
Good!
been thinking about, and
Oh,
I
I'm sorry. I'm sorry to affect your brain in that way. Go ahead.
When we calculated the average, the mu,
Yes,
for
the one die.
1 out of 6,
Yes,
it
ma'am.
was 3.5.
3.5.
What does that mean?
So, great. So what Aaron is troubled by, I got 2 answers for you. If that's okay, I got 2 answers for you, if that makes sense. So Aaron's troubled by the fact that when we averaged 1 die, the average was 3.5. And her great question was, what does that mean? So, if I may, I would answer 2 ways. First is a real quick mathematical way. What was the average for 2 dice? The sum.
7.
7. Did that bother you at all? You can say yes. No, it was okay. And I probably didn't bother you, I'm guessing, because 7 was actually one of the outcomes. Like 7 was one of the numbers in that list, correct?
Well, I think it didn't bother me because the probability, the frequency
is so high.
they're all different.
Yes, but when they're all the
When
same.
they're all the same, I don't
Okay,
understand why.
so check this out. How many dice make up this average?
12.
No, how many dice did you roll to get that average? 2.
Two.
So 3, and the 2 dice are exactly the same, correct?
Yeah.
So one of them should contribute half of the average, the other one should contribute the other half of the average, right? Does that make sense?
Yeah.
So one die contributes half of the 7, or 3.5. The other one contributes the other half of the 3.5. Now, of course, that's a bit of a bastard answer, because we can only answer it that way after we've done this experiment. So how do you answer it from last week with only one die? So let me come back to a more mathematical answer for you there. What is an average at the heart of what an average is? I wish Sarah was here. She gave me that great definition of what it was last week. You see, the balance point of the cookie crumbs, yes?
Yep.
So where would I have to put this to balance it? Nowhere to stop.
In the middle.
You have to define middle. It's one of those things. Like, what is middle? Middle is balance for an average, right? Now, what does the distribution for one single die look like? Well, that's what the pie chart looks like.
Same.
It's exactly the horizontal. Well, if you're looking at a tray of cookies where there are 6 columns and the same number of each column, where would you have to put your finger? Directly in the middle. But directly in the middle, if you try to pick a 4 or a 3 to go to, it's going to fall to one side because you have more weight. Directly in the middle puts 3 over here, 1, 2, and 3, and 4, 5, and 6 over here, which puts your finger directly between the 3 and the 4. So mathematically, it's 3 and 3.5. That doesn't mean you can roll a 3.5. It just means for every 3, you're going to roll a 4 some other time. And for every 5, you're going to roll a 2 some other time. And for every 6, you're going to roll a 1. So it's about the balance point. Think of it as a balance point. And that'll make sense that sometimes it has to be those goofy like 3.5s and things. The same thing happens with 3 dice. When you roll 3 dice. I'm not quite buying it yet. That's okay.
No, I mathematically I understand how it works, but I just don't see how it applies,
So,
what it actually means.
you guys ready? No, we can't do enough trials to make it believable. So here's the deal. But I'm gonna let's try it a different way. Madeline, roll 1 die for me. She rolled a 5. With the same probability, someone else is gonna roll a 2. Because they're both 1 in 6, right? They both have a 1 in 6 chance. So if I take Madeline's 5 plus the other person's 2 and average those 2 together, I get 3.5, don't I? Because 5 plus 2 is 7, 3.5. Brandy, if you would,
Yeah.
just 1 die. 5, do it again, do something different. 1 in 6 chance, it happened, it happened!
5.
Damn it! Brandy, you're fired!
3.
There we go, 3. With equal probability, somebody else is going to roll a 4.
Yeah.
So 3 plus 4 is 7, divided by 2 is 3.5. Every time anybody rolls something, even Brandy who rolls 5s all the time, there's going to be somebody else somewhere else rolling the complement to get to 7 from that. So it's going to balance out to make 3.5. So just let it wash over you some more.
Okay.
If you get the mathematics, that's huge. The context will come. It's kind of like saying in 1990 there were 2.5 children per family in America. What? All it means is, out of every 10 families, there are 25 kids. Divide 25 by 10, you get 2.5. An average of 3.5 per single die roll means out of every 10 die rolls, we've rolled 35 sums of numbers that divide to make 3.5. It's all it is. It's an accumulated... That makes more sense. Okay, good. I saw that. That one registered better. Good! I just hit you with as many different explanations as possible. One makes sense. Good! So it's basically an accumulated average over time. For every 1, there's a 6. There you go. Beautiful. That makes me happy. That makes me very happy. Steven, go.
I just had an analogy that.
Good. Do it.
Let's say you go and buy a pizza,
Oh, see, I'm
and
hungry.
it's cut into 7 pieces, and there's 2 of you eating it. You each get 3 pieces, but there's 1 piece left.
Oh, that's clever. What are you going to do with that 1 piece?
You eat it before the other person.
You eat it before the other person does.
Yeah.
I got another question. Who the hell can accurately cut 7 pieces of pizza? What angle would that be? As an Italian, that impresses the hell out of me. 8's easy. Boom, 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 boom. 22.5 degrees. 7 does not divide into 360. No, it's a brilliant analogy, though. Did you catch that analogy?
Yeah.
You take
and I
3, you take
understand
3,
the
there's-
math and all
Good.
everything. I just didn't understand how it Like what it actually means to get
Absolutely.
3.5.
Absolutely. It's that long run over time. Or long pizza over round.
I think I was
It's
thinking
quite
of
good. I
like,
like that a lot. I don't remember
if
that.
you, I was thinking of the way you, the average as like
Share?
equal, yeah, equal share,
Mhm.
but they're already all equal share.
But you could, so here's the deal. Oh, I love this. You're giving me another way to talk about it. So, when Brandy rolled her, oh, shit. So here we go.
But this is the
1,
average
2,
of
3,
the
4, 5,
sum.
6. No, this is perfect. You got it. You got it. You got it. Actually, let me draw a picture to explain. This is a perfect way of explaining. I haven't thought about this before. So we know equally you're going to get either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. This is a beautiful way of doing it. So now we know that I can put one of each of those up there because they all have the same frequency. I don't have to put 2 1s and 1 2 because they're both 1/6. So now, to make it an average, I have to share those dots. So I've got to take one of those dots and move it over here, just to share. This is the lollipops from the first week of class, right? Then I've got to take one of those and we put it over here too. We're getting close, right? Maybe I should take one of these guys and give it to this guy over here, right? But now I'm in a problem, aren't I? I'm at a problem because 3 of them have 3 and 4 of them have 4. Excuse me, 3 of them have 3 and 3 of them have 4. So what I should do now is I should take half a dot here and give this guy half a dot. Same thing here, yes? And then same thing here. And now they all have 3.5 dots. That, combined with the pizza, you guys just gave me 5 minutes of beautiful pedagogy I would have never thought to use right here. Thank you for that, and I'm glad we're recording it. That's a perfect way of explaining it. A beautifully perfect way of explaining it. Thank you. I wouldn't have thought to make that back connection back. It's the lollipops all over again. Now, what the distribution allows us to do is it allows us to weight them. With a single die, they're all weighted equally, so you just put 1 of each. With a double die, you have to put 1 2, 2 3s, 3 4s, 4 5s, and so forth. And it becomes too tedious to do it this way. But for one die, it's gorgeous. Oh!
Okay, thank
Both
you.
of you. Thank you, both of you. Thank you guys. That was awesome. So glad I got recorded because that is like the most beautifully simplistic, understandable way, beyond mathematically, to understand it. Oh, good. Very, very good. That is so great. Totally
That
great.
makes sense now.
Other questions? I'm so glad that question came up. Other questions? Just a show of hands. For how many of you did that really clear it up? That Aaron's idea right there. That just makes me stoked. That makes me so stoked. And the same thing can be applied for any distribution with the proper weights. Oh, good, good, good. That pizza thing. Okay, we have probably enough time to collect some data, if not analyze it. That's okay. You also have a coin in front of you, yes? Here's the next experiment. It's going to be related to something we